Man, I'm gonna need a translator or something because she might as well be speaking French. I can't deal with this. Is class almost over yet? I feel like I've been in here forever. Man, it was a late night last night. Is class over yet? Integration? I didn't think this was history class.
Boy, what you talking about?
Hey. Man, what is this squiggly S-shaped thing in front of the equation? Man, is she done yet? I'm hungry. I'm tired. Crap. I think I have finals in a week. Should probably learn this stuff. Nah. I'm gonna have to cut this French lesson short. Au revoir.
Wake up!
Gosh, I hate derivatives. How does any of this apply to the real world?
So you want to know how this applies to the real world, huh? How about we take a little trip to a car sale?
What kind of car are you looking for?
So, we're looking for a car that's hot, that's a convertible, and that's fast.
Alright. Well, I think I know what you're looking for. You might want the Pontiac G6 GT. This car's got hot curves, hardtop convertible, and 50 meters per second squared acceleration.
I don't know about that. That's a bit faster than Formula One car accelerates.
I think we're gonna need to take this one for a test drive.
Yeah, sure. Don't scratch the paint.
Let's do this.
Let's go.
Cut.
You got about 2 seconds for that car, man.
We're going to graph our data collected from our speedometer. We're going to measure it in time intervals of 2 seconds at t equals 0, t equals 2, t equals 4, and t equals 6. At t equals 0, we have 0 miles per hour and 0 meters per second. At 2, we have 29 miles per hour and 12.96 meters per second. At 4, we have 37 miles per hour and 16.54 meters per second. At t equals 6, we have 60 miles per hour and 22.33 meters per second. Now we are going to graph this data. On the x-axis, in intervals of 2, we have our time measured in seconds. And on our y-axis, in intervals of 5, we have our velocity, which is measured in meters per second. Now we're going to graph our points. Now we're drawing our acceleration curve. Now we're going to find our acceleration. We're going to do 22 minus 0, and we're going to do 6 minus 0, which is our slope, also known as change your y and change your x. And that's going to give us 3.67 meters per second squared, which is our acceleration.
Using our understanding of the relationship with velocity and acceleration, we were able to determine that the salesperson was not being honest about the car's actual general acceleration. Now I'm going to talk to you about the relationship of derivatives with graphs. The first relationship is if d, the distance, remains constant. This graph basically is telling someone that the object is not even moving. So if the object is not moving, or changing distance, it does not have a velocity and it does not have an acceleration. Now let's say that the object is progressively moving away from the point of origin. That means that the object would have a constant velocity. But if an object has a constant velocity, that means that an acceleration does not exist in the object. The last scenario I'd like to talk about is in the hypothetical situation that the object was moving away from the point of origin exponentially. If that's the case, then the derivative, which would be the velocity, would be increasing. And if the velocity is increasing, that means that the derivative, the acceleration, is positive. And that is the relationship of derivatives with graphs. Alrighty, so I'm going to first talk about how to find the derivative of just a single variable. So we have this basic equation here, f of x equals x to the n power. Now, to find the derivative of this, we simply take n, bring it down, make it a coefficient. Then we have our variable x. And then our new power will be to the n minus 1. So an example of this would be f of x equals x squared plus 1. Now, referring back to this little formula right here, we see that the derivative of f of x is going to equal 2x. Why? Because n equal to 2, so the 2 becomes a coefficient, just like n became the coefficient here, and we see that the new degree is n minus 1. 2 minus 1 is 1. We're not going to waste the time putting a 1 up there. It's just naturally assumed. Now, you might be wondering how this 1 just magically disappeared. Well, because it's a constant, it's not a variable. Constants don't continue on when you find the derivative of functions. Next to look at is the chain rule. You use the chain rule when you're trying to find the derivative of two variables when they are multiplied together. Just remember, first times the derivative of the second plus the second times the derivative of the first. For example, f of x is equal to x squared times x cubed. So in order to find the derivative of this function, first x squared times the derivative of the second, x cubed, which ends up being 3x squared, plus the second, x cubed, times the derivative of the first, which ends up being 2x. Now, we're going to look at the quotient rule. And you use the quotient rule when you are dividing two variables and you need to find the derivative of the function. The thing to remember for the quotient rule is low d high, low meaning the variable on the bottom, times the derivative of the variable on the top, thus low d high, minus high d low, all over low low. For example, f of x is equal to x squared divided by x cubed. The derivative of f of x is going to equal low x cubed times d high, 2x, minus high, which is x squared, d low, which is 3x squared, all over low low, which is x cubed squared. Last but not least, I'm going to talk about how to find the tangent line. The problem will present you with an equation and a set of points. For example, f of x equals x squared at point 2, 2. And they will ask you to find the tangent line of this particular point. First, you have to find the derivative of the equation. So the derivative of the equation that I just presented in the example is 2x. After that, you will then plug in your x value from your point to find your slope of the tangent line. So our x value in the point was 2. So what we do is we just plug in 2. 2 times 2 gives you 4. The final step is that you then plug in your values into the point slope form. Point slope form is y minus y1 equals m times x minus x1. So we simply plug in our points. Y minus 2 equals 4, which was our slope that we found in the last step, times x minus 2. And that is how you find the tangent line of a point.